Welcome back to day 3 of chapter 1. We are going to be entering section 1.2 today, looking at dot plots, describing shape, comparing distributions, and creating stem plots. By the end of this lesson, you'll be able to make and interpret dot plots and stem plots of quantitative data, describe the overall pattern, shape, center, and variability of a distribution, and identify any major departures from the pattern outliers. So major departures, outliers, but also other things. Identify the shape of a distribution from a graph, compare distributions of quantitative data using dot plots or stem plots. And again, this is the assignment that you should complete after this lesson. Let's dive in to our first page. All right, so we're looking at 1.2 day 1, displaying quantitative data with graphs. And you can read much of this information on pages 30 to 37 in your book. Now, as you learned in the last 2 lessons, we use a bar graph or pie chart to display the distribution of a categorical variable. Now, the bar chart could be a regular bar chart. It could be side-by-side bar charts. It could be segmented bar graphs. It could be a mosaic plot, all right? Bar graph of some type or a pie chart. Now we're going to explore how to display the distribution of a quantitative variable. Although there are several types of graphs that can be used to display quantitative data, one of the simplest graphs to construct and interpret is a dot plot. Right? A dot plot shows each data value as a dot above its location on a number line. We were making these all through chapter 4 in our activities. So hiring discrimination, we created a dot plot. In our get your heart beating activity, we created a dot plot. We were doing these with some frequency. Now let's take a look at how to formally do this. So how to make a dot plot. Step 1. Draw and label the axis. So draw a horizontal axis and put the name of the quantitative variable underneath. Be sure to include units of measurement for continuous variables. Step 2, scale the axis. Look at the smallest and largest values in the data set. Start the horizontal axis at a convenient number equal to or less than the smallest value and place tick marks at equal intervals until you equal or exceed the largest value. Now, when we were doing our get your heart beating activity, I asked each of you who had the lowest. We went through and figured out who had the lowest, and I figured out a number that was very close to that would be easy for me to scale by. And then I figured out who had the highest. So I knew if I had to go by 5s or by 10s or something like that. All right, so that was me modeling how to scale an axis. Once you have things scaled, then you plot the values. So mark a dot above the location on the horizontal axis corresponding to each data value. Try to make all the dots the same size and space them out equally as you stack them. All right, so let's go ahead and follow these steps with the following example. For example 1, here are the data on the number of goals scored in 20 games played by the 2016 U.S. women's soccer team. All right, so we have 5, 5, 1, 10, 5, 2, 1, 1, 2, 3, 3, 2, 1, 4, 2, 1, 2, 1, 9, 3. Now, I didn't bother to put these in order. I noticed that my lowest number was 1, my highest number was 10, so I decided to go ahead and start at 0, and just numbered by 1s, going on up. I wrote down number of goals scored, so my number line was drawn, I labeled it, I scaled it, and then, starting with a 5, I put a dot at the 5, another dot above it. I put a dot at the 1 at the same level as the original dot. I put a dot at the 10, another dot at the 5, 2, a dot above the previous one, making sure I was staying at the same width as I was going through, so keeping dots of comparable numbers at the same height. Another 1, another 2, and so on until I had all of these numbers filled in. All right, that's how I created my dot plot. Now, things to remember, making a graph is not the end of your analysis. All right, the graph is a good place to start. It lets us see what we're working with. But when you look at a graph, you should ask, what do I see? All right, so how do we start a description of what we see in a quantitative graph? How do we put it into words? We begin by describing the shape of the distribution. Now, when you describe the shape of a dot plot or another graph of quantitative data, we focus on the main features. So look for major peaks, not minor ups and downs. Looks like we have a major peak here. This would be considered a minor up and down. This would just be single peaked. right? So we don't look at minor ups and downs. We look for clusters of data values. It looks like most of the goals are clustered between 1 to 5. There are 2 goals much higher than that at 9 and 10, right? And we look for obvious gaps. There is a gap definitely between 5 and 9. Now, this says it should say decide if, so excuse my typo, decide if the distribution is roughly symmetric or clearly skewed. Now, roughly symmetric would mean that the left side of the graph, if you were to fold it in half, is close to the same as the right side of the graph. Now, your peak could be in the middle. You could have 2 peaks on either side, but you should be able to draw a line through the middle of your values and fold the graph almost perfectly in half on top of itself. This is not that. This one looks to be skewed, and specifically it looks like there are a few data points pulling away from the majority of them to the right, which is one of the things that's making this skewed to the right. Now, we would describe it as roughly symmetric or clearly skewed. Now, distributions seldom have perfect shapes. Use LY words, so Lee words, to modify your description of the shape. Roughly symmetric, slightly skewed to the right, strongly skewed to the left, things like that. Notice that these words end with LY. That's what I mean by Lee words. Okay, let's go to the next page. Now, this next page has different descriptions of symmetric, skewness, just ways to recognize shapes and distributions. So roughly symmetric means that from your center of your distribution, your points they vary about the same amount on either side of the center. So a distribution is roughly symmetric if the right side of the graph containing the half of the observations with the largest values is approximately a mirror image of the left side of the graph. Right skewed. All right, take a look at this. Do you see how the center of the distribution seems to be stretching more to the right? All right, so a distribution is skewed to the right if the right side of the graph is much longer than the left side. All right, see how much longer this is? Skewed left. A distribution is skewed to the left if the left side of the graph is much longer than the right side. So find where your center is and then look to see how much longer the graph is on the left versus the right. Longer on the right, skewed right. Longer on the left, skewed left. Right and left refer to larger values versus smaller values. Skewed left is always skewed towards the smaller values. Skewed right is always skewed towards the larger values. Unimodal. So the distribution of a quantitative variable is unimodal if it has a single peak. The distribution of a quantitative variable is bimodal if it has 2 distinct clusters or peaks. All right, mode refers to how frequently, basically the number with the most frequency. So unimodal, one mode. Notice that 20 occurs the most often. This is unimodal. Double peak, there are 2 major peaks on this and 2 distinct clusters. So this is bimodal. If you were to trace over this, you would have 2 distinct peaks on this graph. Now, uniform means that there are absolutely no peaks. Right? The distribution of a quantitative variable is approximately uniform if the frequencies are about the same for all values. Notice there's only a couple different. As you go across, they're almost the same. Right? This would be approximately uniform. Things are very rarely completely uniform. Let's take a look at our next page. And how do you describe a distribution of a quantitative variable? Let's consider the following example. Right, so how to describe distribution of a quantitative variable. In any graph, look for the overall pattern and for clear departures from that pattern. So you can describe the overall pattern of a distribution by its shape, center, and variability. An important kind of departure is an outlier, an observation that falls outside of the overall pattern. Now, an AP exam tip, always be sure to include context when you're asked to describe a distribution. This means using the variable name, not just the variables, the units the variable is measured in. So for example 2, describe the distribution of goals scored in 20 games played by the 2016 U.S. women's soccer team. So this is the dot plot that I created earlier. For the shape, the distribution of goals scored is skewed to the right with a single peak at 1 goal. There's a gap between 5 and 9 goals. So we've described whether it was skewed or symmetric. It's skewed to the right because the data is pulling off to the right. where the single peak is, and the gap between 5 and 9. Outliers. The games when the team scored 9 and 10 goals appear to be outliers. These are definite departures from the cluster of the rest of the number of goals. Center. The median, remember median is the centermost value, is 2 goals scored. So if we were to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right between 10 and 11, since there were 20 games, would be where you would find your middle. That's right in the 2 goals scored. That's how we know that's the median. All right, so the median is 2 goals scored. Variability, the number of goals varies from 1 to 10 goals scored. All right, now, did we include context? Yes. We talked about the goals scored, not just our numerical calculations, and we didn't just include the units. Right? So we included the context. That's really vital. Now, what are the 2 most important things to remember when asked to compare distributions? Context. As shown in the last example, use the variable name as well as units of measurement. And explicitly compare the values. It's not enough to just list values for the center and variability of each distribution. You have to explicitly compare these values using words like greater than, less than, or about the same as. Make sure you provide comparison language. Now, the rest of this can be found on pages 37 to 39. So what is a stem plot, also known as a stem and leaf plot? And what is the most important thing to remember when making a stem plot, and how to make back-to-back, how a back-to-back stem plot is different. So let's start with a stem plot. So a stem plot shows each data value separated into 2 parts. Right? A stem, which consists of all but the final digit, a leaf, which is the final digit. The stems are ordered from lowest to highest and arranged in a vertical column. The leaves are arranged in increasing order out from the appropriate stems. Now, the most common student errors is failing to include a stem that has no leaves and forgetting the key or labels on a stem plot. Just like we have to scale appropriately, I had to include 6, 7, and 8. Even though there were no goals scored there, I couldn't skip from 5 to 9. I had to include the empty numbers. You have to include empty stems. Also, don't forget a key, because that provides context and labeling for your stem plot. We don't label them like we normally do with a number line. So how to make a stem plot. Step 1, make the stems. Separate each observation into a stem consisting of all but the final digit and a leaf, the final digit. Write the stems in a vertical column with the smallest at the top. Draw a vertical line at the right of this column. Do not skip any stems, even if there is no data value for a particular stem. Step 2, we add the leaves. Write each leaf in the row to the right of its stem. Step 3, order the leaves. Arrange the leaves in increasing order out from the stem, so lowest to highest, starting from left to right. And step 4, add a key. Provide a key that identifies the variable and explains what the stems and leaves represent. All right, so let's take a look at how to do this. Now, split stems. So when data values are bunched up, we can get a better picture of the distribution by splitting stems, meaning that we use the same stem twice, once for leaves from 0 to 4, and again for leaves from 5 to 9. Now, how is a back-to-back stem plot different from a basic stem plot? Back-to-back stem plot is a plot used to compare the distribution of a quantitative variable for 2 groups. The values from one group are plotted on the left side of the stem, and the values from the other group are plotted on the right side of the stem. Each leaf is written in the row next to its stem, with leaves arranged in increasing order out from the stem. Now, example 3 takes us through that. Here are long jump distances in inches for 2 athletes. Make a back-to-back stem plot with split stems and compare the distributions. So I have athlete A and athlete B. As you can see, I have one side of my initial stem plot for athlete A, another side for athlete B. I went through and took a look at what the smallest number was in either distribution, and that would be in the 150s. And then the highest number in any of the distributions was in the 180s. I decided to use split stems because there were a lot of numbers in the 150s, the 160s, 170s, 180s, and we only really would have had 4 stems, which is difficult to actually look at the shape. So if we split them, I have 15, 15. That stands for the 150s from 150 to 154. the 150s from 155 to 159, 160s from 160 to 164, the 160s from 165 to 169, 170s from 170 to 174, 170s from 170 to 175 to 179, 180s from 180 to 184, and 180s from 185 to 189. For athlete A, I started writing in for the 150s. I had 154, so the 150 part is the 15. The 4 is what's in the leaf. 157, 150, and then 7 here. Because this would be from 5 to 9, it goes in the second split stem. 187 goes in the second split stem down here. That's why I have the 7 here. The 3 from 163 went up in the first stem for the 160s. 167 went in the second stem for the 160s. 159 went in the second stem for the 150s, and so on. I did the same thing with athlete B. Now notice that these are all jumbled up. It's easiest sometimes to start writing out your stem plot first, and then write your final stem plot with everything in order. So I have the same stems. I still have athlete A, athlete B, but I rearranged my leaves so that they were going in order from least to greatest out from the stem. So I have 1 and then 4, 7 and then 9, 2 and then 3. So this would represent 151, 154, 157, 159, 162, 163, 165, 165, 167, 169, 174, 175. It's now going in numerical order. On the other side, we have 152, 153, 153. This athlete had a long jump of 153 2 separate times. That's why I have 2 different 3s, one for each of the long jumps that measured that amount. And then I have my key down here that says 16, and then a line, and then 2 is a long jump distance of 162 inches. Now to describe these and to compare them, athlete A's long jump distance in inches are roughly symmetric, while athlete B's long jump distances in inches are skewed to the left. Notice I'm including the context. Both are single peaked. Athlete A's long jump distances have a greater center than athlete B's, with a median of 167 inches versus 162 inches respectively. Athlete A's long jump distances are also vary more, 151 inches to 187 inches, than athlete B's long jump distances, 152 inches to 169 inches. Neither distribution of long jump distances appears to have outliers. So I've described the shape, the center, variability, and whether or not there are any deviations from the majority of the data. This is how you compare using specific comparison language. All right. This is the assignment I would like for you guys to work on when you get to class, and I will see you in class. That's it.